Hello everyone. Today I'll be presenting section C of our second internal test of data science, deep learning, which covers question from question number 26 to question number 40. This presentation is submitted to Dr. Shaligram Prajapat sir, and my name is Athar Chauhan. My roll number is IC2K2315. Let's begin by understanding what deep learning really is and why it has become so important today. So let's begin. Now, understanding deep learning. Deep learning is a part of machine learning, but it goes deeper, literally. It uses multi-layered neural networks that learn patterns directly from data without needing us to manually program those patterns. Deep learning is behind many technologies we use every day, like face recognition, speech assistants, chatbots, autonomous cars, even advanced medical diagnosis systems. So let's start with our first question, question number 26. Deep learning is a subset of machine learning, is our question. Sorry, it's an answer. The first concept is simple. Deep learning is a specialized subset of machine learning. That makes it special is its use of neural networks inspired by the human brain to learn complex patterns and representations. Our next question. Neural networks are universal approximators. This means that they can approximate almost any mathematical function if trained with enough data and neurons. That's why they power high level tasks like image recognition, predictions, and decision making. Our next question. A network with more than one hidden layer is called a deep neural network. Yeah, each layer learns something new from simple patterns like edges to complex objects like faces. This layered learning gives deep learning its power. Question number 29. Each layer's output becomes the next layer's input. In neural network, each layer's output becomes the next layer's input. This process is called as forward propagation, and it helps the model gradually build more meaningful features from the raw data. Question number 30. Convolutional neural networks or CNNs are mainly used for image classification. They use filters to detect edges, textures, shapes, and complex objects. Because of weight sharing, they use far fewer parameters than fully connected networks, making them efficient and fast. Now, recurrent neural networks. Recurrent neural networks handle data that change with time, meaning they capture temporal dependencies. They are great for tasks like language understanding, speed recognition, and time series. Forecasting because they remember past information while processing new inputs. Next question. Long short term memory networks, in short form LSTM, is an improved version of recurrent network. LSTMs are improved version of RNNs. They solve the vanishing gradient problem using gates, forget input and output gates, which help the network remember information for long periods. This makes them excellent for long text, long sequences, and complex patterns. Now, generative adversarial networks. In GNNs, the second model acts as a discriminator, distinguish real and fake data. The generator creates fake data and the discriminator tries to detect whether it's real or fake. This competition makes both models strong, leading to very realistic image and audio generation. Question number 34. Transfer learning. Reusing a pre-trained model for a real task is called transfer learning. It saves time, reduces training cost, and works especially well when we have a small data set. Question number 35. The wide part helps the model memorize specific patterns or interactions. This is very helpful in recommendation systems where past user behavior is essential. Question number 36. The deep part of the model captures generalized patterns. It looks beyond exact matches and learns hidden relationships, making the model more flexible and powerful. Question number 37. Linear classifiers. Linear classifiers combine inputs using weights and biases. They create a simple straight line decision boundary which forms a foundation for many more advanced models. Now, question number 38. Activation functions add non-linearity. Activation functions add non-linearity to neural networks. Without them, a neural network would just act like a linear model. Functions like ReLU, sigmoid, and 10H help the model learn complex patterns. Question number 39. Model capacity. Adding more layers or neurons increases model capacity. While this helps learn complex patterns, too much capacity can lead to overfitting, where the model memorizes instead of generalizing. A last question for this section. Transfer learning leverages prior knowledge. Transfer learning leverages prior knowledge. It uses learned weights from previous tasks, allowing new models to start from a strong baseline and perform better with less data. Yeah. So, uh, for the key takeaways, to summarize, deep learning is a powerful part of machine learning. Neural networks can approximate complex functions. CNNs power vision, RNNs handle sequences, GANs generate realistic content. Transfer learning speeds up training. Wide and deep models, mixed memory and generalization. Activation functions add intelligence to neural networks. So, yeah, thanks for watching. I hope you like my video. Deep learning may seem complex, but once you understand these building blocks, the rest becomes much more easier. Thanks for listening.